What specific problem does the Matryoshka quantization method aim to solve regarding deep learning model inference?
The Matryoshka Quantization (MATQuant) method aims to address two specific challenges in deep learning model inference: the high decode latency associated with large language models (LLMs), and the inefficiencies in current quantization techniques that treat each target precision as an independent optimization problem. By leveraging the nested structure of integer data types, MATQuant allows for the simultaneous optimization of model weights across multiple precision levels, e.g., int8, int4, int2, enabling the extraction of accurate lower precision models from a single trained model. This approach not only reduces the overall communication load during inference, but also significantly improves the accuracy of extremely low precision models, such as int2, which typically suffer from high inaccuracy when trained independently. Ultimately, MATQuant facilitates the development of versatile models that can operate effectively at various bit widths, providing a flexible accuracy versus cost trade-off for efficient LLM inference.
Can you explain how the proposed MATQuant method works? Please illustrate the steps involved in multi-scale training and weight quantization for varying integer precisions.
The proposed Matryoshka Quantization (MATQuant) method operates by leveraging the nested structure of integer data types to enable multi-scale training across varying integer precisions, specifically int8, int4, and int2. The process begins by training a single model that optimizes the quantization loss for multiple target bit widths simultaneously, allowing for the extraction of lower precision models from a higher precision model by slicing the most significant bits, MSBs. For instance, to obtain an int4 model from an int8 model, the top 4 bits are retained while the rest are discarded, effectively creating a new model without additional training. MATQuant employs a joint optimization strategy where the model parameters are shared across different precisions, thus enhancing the performance of lower precision models, particularly int2, which benefits from the higher valued weights that are more prevalent in the quantized weight distributions. This method not only improves accuracy across all targeted precisions, but also allows for the seamless extraction of interpolative bit widths, such as int6 and int3, by utilizing the same slicing technique, thereby providing a flexible and efficient quantization framework for large language models.
Could you provide a simple example that demonstrates the inner workings of the MATQuant algorithm, particularly how it extracts models from the quantization process?
The Matryoshka Quantization (MATQuant) algorithm operates by leveraging the nested structure of integer data types to extract models of varying precisions from a single quantized model. For instance, if we have a model quantized to int8, we can extract an int4 model by slicing the most significant bits, MSBs, of the int8 weights. Specifically, this is achieved through a right shift followed by a left shift, which effectively retains the top bits needed for the lower precision model. The algorithm optimizes the quantization loss across multiple bit widths simultaneously, allowing for the creation of models like int2 from the int8 model without the need for separate training. This process not only enhances the efficiency of model deployment, but also ensures that the extracted models maintain high accuracy, as demonstrated by the significant performance improvements of int2 models generated through MATQuant compared to those trained independently.
What are the theoretical and practical benefits of using MATQuant for quantization of large language models compared to traditional methods?
Theoretical benefits of using Matryoshka Quantization (MATQuant) include its ability to leverage the nested structure of integer data types, allowing for the simultaneous optimization of model weights across multiple precision levels, int8, int4, int2, within a single model. This contrasts with traditional methods that treat each precision as an independent optimization problem, resulting in distinct models rather than a versatile one. Practically, MATQuant demonstrates significant improvements in accuracy, particularly for int2 models, which outperform independently trained counterparts by up to 8% on downstream tasks. Additionally, MATQuant facilitates the seamless extraction of interpolative bit widths, e.g., int6 and int3, and enables layer-wise mix-and-match of different precisions, providing a flexible accuracy versus cost trade-off. Overall, Mat-Quant enhances the efficiency of large language model inference by producing adaptable models that maintain high performance across various quantization levels.
How was the effectiveness of Mat-Quant validated in the experiments? What specific datasets and metrics were used to demonstrate its performance?
The effectiveness of Matryoshka Quantization, Mat-Quant, was validated through empirical evaluations on standard large language models, LLMs, such as Gemma 2, 2b, 9b, and Mistral 7b, focusing on the feed-forward network, FFN parameters. The experiments utilized the C4 dataset, with metrics including log perplexity and average zero-shot accuracy across various downstream tasks, such as ARC-C, ARC-E, Bool-Q, HeliSwag, Pika, and Winagrande. Results indicated that Mat-Quant produced int8 and int4 models with accuracy comparable to independently trained baselines, while significantly improving int2 models by 4.37% to 8.01% in accuracy across different model sizes. Additionally, the models trained with Mat-Quant demonstrated strong interpolative performance for bit widths not explicitly optimized during training, such as int6 and int3, further showcasing its versatility and effectiveness. Overall, the experiments highlighted Mat-Quant's ability to achieve high performance across multiple quantization levels while maintaining efficiency.
What limitations or drawbacks did you identify in the Mat-Quant approach, particularly in terms of model generalization or computational efficiency?
The Matryoshka Quantization, Mat-Quant approach, while innovative, does have some limitations regarding model generalization and computational efficiency. One notable drawback is that the int2 models generated by Mat-Quant, although significantly outperforming their independently trained counterparts, still exhibit a slight accuracy drop when compared to the int4 and int8 models due to the need to balance performance across multiple precision levels. Additionally, the method's reliance on shared most significant bits, MSBs, may lead to overfitting, particularly in scenarios where the training data is limited, as seen with the COT method, which can suffer from severe overfitting to the dataset used. Furthermore, while Mat-Quant allows for flexible model extraction across bit widths, the computational efficiency may be compromised when optimizing for multiple precisions simultaneously, as the joint optimization can complicate the training process. Lastly, the stability of quantization at lower precisions, particularly for int2 and int3, remains a challenge, indicating that further refinements are necessary to enhance the robustness of the approach in practical applications.